Geometric Physics 1, Lecture 9, Magnetic Terms and the Poincaré Lemma. Today's reading is Marsden and Ratiu, sections 6.6 and 6.7, with Frankel chapter 5 and sections 16.4 A and B. For next time, read Marsden and Ratiu, chapter 7, sections 1 through 4. Two threads meet today. One is pure topology. The other is a charged particle. They turn out to be one thread. Two questions today, from opposite ends of the course. The first is topological. Checking that d alpha vanishes is a computation. When does it follow that alpha is d of something? Lecture 7's Moser argument needed that, and so did Lecture 8's generating functions. Both bought it on credit. Today we pay. The second is mechanical. On t star q, omega equals minus d theta. What if we add to omega a closed 2 form, pulled up from the configuration space? The route has 5 stops. First, the Poincaré Lemma. On a contractible region, closed implies exact, and we get a formula for the potential. Second, the two standard failures, the punctured plane and punctured R3. Third, the magnetic form omega sub b, symplectic for every closed b. Fourth, Fibre translation by a one-form A, and what happens when no such A exists. Fifth, the Lorentz force, derived 3 times. Now the sentence to keep. A magnetic field is a closed 2 form on the configuration space. The question is where to put it, inside H or inside omega. When B is exact, you may choose, and the choice is gauge freedom. When B is not exact, only omega will take it. First, the topology, closed forms, exact forms, and the one theorem that tells you when a closed form has a potential. Fix a manifold and a degree k, at least 1. A form alpha is closed if d alpha vanishes. It is exact if alpha equals d beta for some beta of 1 degree lower. Exact implies closed, always, because d of d is 0. That was lecture 3. The converse is the whole subject. Its failure is measured by Dirac cohomology from lecture 4. The k-th cohomology is the closed k-forms modulo the exact ones. We are carrying 2 debts. Moser's trick needed omega minus omega naught to be d of something on a ball, and lecture 8 wanted theta minus the pullback of theta to be d of a generating function. Both are the same theorem, and both were stated only locally. A warning about the name: Frankel calls d of d equals 0 itself the Poincaré Lemma, and calls the real statement its converse. Marsden and Ratiu attach the name to the real statement, and so do we. Now the sentence to keep. Closed is a differential condition. It is local, checkable in one chart, verified by differentiating. Exact is a claim of global existence. It says that 1 beta works everywhere at once. Everything today lives in that gap. Here is the theorem. A region is called contractible if its identity map is smoothly homotopic to a constant map. Concretely, there is a smooth family of maps from the region to itself, starting at the identity and ending at a single point. Every star-shaped set is contractible because you slide radially to the center. The Poincaré Lemma says this. Let U be contractible and let K be at least 1. Then every closed K form on U is exact. If d alpha vanishes, then alpha equals d beta on all of U. Equivalently, all cohomology of U above degree 0 vanishes. 2 things to notice. The hypothesis is on the domain and never on the form. Nothing whatever is assumed about alpha beyond closedness. And every point of every manifold has a star-shaped chart neighborhood. So every closed form is locally exact, always. Now the sentence to keep. Closed equals exact is never a statement about the form. It is a statement about the shape of the region. The lemma has content only because we ask for 1 beta on all of U at once. The first failure is the cheapest. Take the plane with the origin removed. On it put the one form alpha equal to x dy minus y dx all over x squared plus y squared. 2 derivatives show that d alpha vanishes, but the integral of alpha around the unit circle is 2 pi. If alpha were d of a function, then by Stokes from lecture 4, that integral would vanish since the circle has no boundary. So alpha is closed and not exact, and the first cohomology of the punctured plane is one-dimensional. Restrict alpha to a contractible piece, say the plane slit along a ray, and it does become exact. The obstruction is purely global. A note on notation. Everyone writes alpha as d of the polar angle, and that is an abuse. The polar angle is not a function on the punctured plane, only a function up to multiples of 2 pi. And theta is never the angle here, since theta is the tautological one form. Now the sentence to keep. The obstruction is a number, the period of alpha around the hole. One hole, one period, one dimension of cohomology. Deleting one point from the plane already breaks the Poincaré lemma. The second failure lives 1 degree up. Lecture 4 built the solid angle form on R3 with the origin removed. Its numerator cycles x dy wedge dz through the coordinates, and its denominator is the cube of the distance from the origin. That form is closed, and its integral over the unit sphere is 4 pi. So it is not exact, and the second cohomology of punctured R3 is one-dimensional. Degree matters here. On punctured R3, the first cohomology vanishes, so every closed one form there is exact. The failure sits in degree 2 only, just as on the punctured plane it sat in degree 1 only. A puncture obstructs in the degree that sees the sphere it leaves behind. And here is why we care. The solid angle form is a closed 2 form on a configuration space, and it is the field of a magnetic monopole. Later today, it defines a symplectic form with no global vector potential. Now the sentence to keep. The standard counterexample in degree 2 and the field of a magnetic monopole are the same object. Lecture 30 turns the period over the sphere into Dirac's charge quantization condition. The proof of the lemma is constructive, and the construction is Cartan's magic formula again. Let U be star-shaped about the origin. For a p-form alpha, define a form of degree 1 lower, called k alpha. Feed the position vector into the first slot of alpha, evaluate the coefficients along the ray to the origin, and integrate against a power of t. The theorem is one identity of k alpha plus k of d alpha equals alpha. If alpha is closed, the second term dies, and alpha is d of k alpha. The proof in one breath. Let h of t and x be t times x, the identity at time 1 and the constant map at time 0. Cartan's formula from lecture 5 then finishes it. For a one form, the recipe is familiar. K alpha is the line integral of alpha along the straight ray from the origin. Path independence is exactly what closeness is doing. Now the sentence to keep. K is a chain homotopy between the identity and 0, and dk plus kd equals the identity is the whole lemma in one line. Contractibility is what makes K exist, and nothing else is used. Let us turn the crank. On R3, take B equal to B naught times dx wedge dy, a uniform field along the z-axis. Apply the homotopy operator with P equal to 2. Out comes A equal to 1/2 B naught times the quantity x dy minus y dx. Differentiate and you recover B. Physicists call that the symmetric gauge. The homotopy operator did not guess it. It produced it. Another primitive of the same B is B naught times x dy, the Landau gauge. The difference between the two is d of minus 1/2 B naught xy. That is no accident. If two forms have the same exterior derivative, their difference is closed, and on a contractible region, the lemma makes it d of something. So primitives are unique up to d of a function and never more precisely. Now the sentence to keep. The known uniqueness of the potential is the gauge freedom of physics, which lecture 4 showed you as A going to A plus d chi. The homotopy operator makes one choice. Nature makes none. The rest of the hour is about what happens when there is no choice to make. Second movement, we push a closed 2 form up from the configuration space onto the cotangent bundle, where it deforms the symplectic structure. Here is a construction almost too simple to name. Let A be a one form on the configuration space. Fibre translation by A sends a covector alpha sub q to alpha sub q plus A at q. It slides each fiber along itself. It is a diffeomorphism. Its inverse is translation by minus A, and the base point never moves. Now the computation that makes it useful. The pullback of theta under this map is theta plus the pullback of A. The proof is one line. Since the projection is unchanged, the tangent of the projection composed with the tangent of the translation is again the tangent of the projection. So theta simply picks up the extra covector. Apply minus d, and the pullback of omega is omega minus the pullback of dA. Now the sentence to keep. Fibre translations are the second family of natural maps on T star Q. A cotangent lift moves the base and drags the fibers. A fibre translation fixes the base and shifts the fibers. Translation by A preserves theta only when A vanishes, but preserves omega whenever A is closed. By lecture 8, a non-zero closed A is canonical and not a lift. Now the theorem from Marsden and Ratiu. Let B be a closed two-form on the configuration space, and let omega sub B be omega minus the pullback of B. Then the cotangent bundle with omega sub B is symplectic. Closeness first. The exterior derivative of omega sub B is d omega minus the pullback of dB. The first term dies because omega is exact. The second because B is closed. Non-degeneracy is prettier. The pullback of B is horizontal, meaning it vanishes as soon as either argument is vertical. Suppose the interior product of a vector with omega sub B vanishes. Test on a vertical vector. The B term dies, so omega pairs our vector to 0 against everything vertical, which forces it to be vertical too. Now test against anything at all. The B term dies again, and non-degeneracy of omega finishes it. In coordinates, the determinant of omega sub B is plus or minus 1 for every B, however large. Now the sentence to keep. Closeness of omega sub B is exactly closeness of B, and non-degeneracy is free, because the new term lives in the block that omega left empty. The magnetic field modifies the symplectic form, not the Hamiltonian. Suppose now that B is exact, so B is dA for a global one-form A. Then the last two frames collide. Fibre translation by A pulls omega back to omega minus the pullback of dA, which is omega sub B. Equivalently, translation by minus A pulls omega sub B back to omega. So it is a symplectomorphism between the two structures, and as a map, it simply adds A to the momentum. A word on the sign, the only thing here that can trip you. The map carrying the modified structure to the canonical one adds A. The map undoing it subtracts A. The substitution physicists write as P goes to P minus A is the second one. Transporting the dynamics is then automatic. If you replace A by A plus d chi, the two transporters differ by translation by d chi, which is canonical because d of d chi vanishes. Nothing observable moves. Now the sentence to keep. When B is exact, you may keep omega canonical and put the field in H, or keep H free and put the field in omega. A choice of A is precisely a choice of which. That is all the vector potential ever is. Now the case the lecture was built for. Suppose the class of B is not zero in the second cohomology. Punctured R3 with a monopole field is the example. The projection down to the base is a homotopy equivalence since the bundle retracts onto its zero section. So pullback along it is an isomorphism on cohomology. Since omega is exact, the class of omega sub B is minus the pullback of the class of B. Therefore, omega sub B is exactly when B is. Any diffeomorphism induces an isomorphism on cohomology. So if the class of B is not zero, there is no symplectomorphism at all between the modified cotangent bundle and the canonical one. Locally, a potential always exists by the Poincaré Lemma. Cover the base by contractible patches. Choose one on each, and on overlaps the two differ by d of a function. Those functions are a connection on a non-trivial bundle. Now the sentence to keep. When B is exact, the two descriptions are equivalent and A is a convenience. When B is not exact, no global A exists, and only the omega sub B description survives. Lecture 8 sold exactness as the cotangent bundle's extra structure, and omega sub B gives it up. Third movement, a particle of mass m and charge E moving in a magnetic field, done twice, by two roots that agree. Take the configuration space to be R3 and write the magnetic field as a two-form with three components. Closeness of that two-form is exactly the vanishing of the divergence of the field, which we proved in Lecture 4. Root A is the modified symplectic form. Keep the free Hamiltonian and use omega minus E over c times the pullback of B. Here, p is the kinetic momentum, mass times velocity. Root b is minimal coupling. Keep omega canonical and build the Hamiltonian from p minus E over c times a all squared. Here p is the canonical momentum, mass times velocity plus E over c times a. Compare them honestly. Root a needs no vector potential and no gauge choice. Root b needs a global a and depends on it. The two are intertwined by the Fibre translation that adds E over c times a to the momentum. Now the sentence to keep. Same trajectories in the configuration space, different coordinates on phase space. Nothing measurable distinguishes them, and that is what the word gauge means. But root a needs no a at all, so root a is the one that keeps working. Let us derive the Lorentz force. Write the Hamiltonian vector field with components q dot and p dot and contract into omega sub b. The canonical part gives the usual two terms. The magnetic part adds one more. Now match against dH, coefficient by coefficient. The dp terms give the usual q dot equals the derivative of h by p. The dq terms give p dot equal to minus the derivative of h by q minus E over c times b contracted with the velocity. Put in the free Hamiltonian. Its derivative by position vanishes, and q dot is p over m. What is left is mass times acceleration equals E over c times velocity crossed with the field, the Lorentz force. 2 remarks. Only the momentum equation changed. The velocity equation is untouched, which is why p is still the kinetic momentum. And energy is conserved because the time derivative of h is the bracket of h with itself, which vanishes by antisymmetry. Now the sentence to keep. Nobody postulated a force law. We wrote the free Hamiltonian and deformed omega by a closed 2 form. A velocity-dependent force that does no work is simply what a position-by-position term in omega looks like. Take the field uniform along the z-axis. That field is exact, so both roots are open and the equation of motion integrates at once. In the plane perpendicular to the field, the particle goes in a circle at angular frequency EB0 over mc. Along the field, it drifts uniformly, completely untouched. Together, the trajectory is a helix of radius mass times c times perpendicular speed over EB0. Now the Poisson bracket of the modified structure. The positions still commute with each other. Position and momentum still pair to the Kronecker delta, but the bracket of 2 momenta is no longer 0. It is E over c times the components of B. The kinetic momenta have stopped commuting, and the defect is the magnetic field itself. That is the classical shadow of the Landau level algebra. Now the sentence to keep. That bracket is the whole magnetic story in one line, and it is why position and momentum are no longer a Darboux chart. Darboux still applies by lecture 7, so some other chart is canonical. But finding it is exactly finding a vector potential. So, on a monopole background, no such chart exists globally. Last movement. The same physics from the Lagrangian side, and then the doorway into quarter 2. Frankel comes at all of this one floor down on the tangent bundle. A Lagrangian is a function on the tangent bundle. Hamilton's principle makes the action stationary among curves with fixed endpoints, and the condition is the Euler-Lagrange equation. The time derivative of the derivative of L by velocity equals the derivative of L by position. For L equal to kinetic minus potential energy, these are Newton's equations, and with no potential, they are the geodesic equations of the kinetic energy metric. The passage upstairs is the Legendre transform, with momentum the derivative of L by velocity. Lecture 10 does that properly. One convention warning. Frankel's Poincaré 2 form is dp wedge dq, the negative of ours. Every formula of his with an odd number of omegas therefore differs from ours by a sign. Our house convention is fixed for the course. Omega is minus d theta, and the interior product of the Hamiltonian vector field with omega is dh. Now the sentence to keep. Notice what a variational principle will accept. A function on the tangent bundle and nothing else. A magnetic field is a 2 form on the configuration space, which is not a function on anything. The trick is to use A rather than B. A one-form on the configuration space is a function on the tangent bundle, linear on each fiber. So write the modified Lagrangian. Take 1/2 mass times speed squared, subtract the electric potential energy, and add E over c times A evaluated on the velocity. That term is the new ingredient. Differentiate. The momentum is mass times velocity plus E over c times A, the canonical momentum we already met. Feed that into Euler-Lagrange, and the cross terms assemble into the antisymmetrized derivative of A, which is B. Out comes the Lorentz force for the third time. Lujan drew, transforming returns root B, exactly. Now watch gauge freedom appear in 3 places at once. In the potential, A goes to A plus d chi, and B is unchanged. In the Lagrangian, that adds a total time derivative, so the action changes only at the endpoints. In phase space, it is a Fibre translation by d chi, which is canonical. Now the sentence to keep, 3 statements, 1 fact. Gauge freedom is no defect of the formalism. It is the Poincaré Lemma's fine print that a primitive is unique only up to d chi. Where does this go next quarter? A is a connection on a complex line bundle with structure group U1, a rule for comparing fibers over neighboring points. That is lecture 28. B, which is dA, is its curvature, the failure of that comparison to be independent of path. That is lecture 29. Changing A by d chi is a change of local trivialization, not a change of anything geometric. The holonomy around a loop is the exponential of the integral of A around it, which by Stokes is the exponential of the integral of B across it. That is the Aharonov-Bohm phase. The non-exact case has a name too. Punctured R3 with B, a multiple of the solid angle form. No global A, 2 patches, a transition function on the overlap, and a quantization condition. That is the Dirac monopole, built in lecture 30. Now the sentence to keep. Everything today was the abelian curvature, only shadow of the connection story. The modified cotangent bundle is our first symplectic manifold built out of a curvature. And the Poincaré lemma says precisely that a connection is always locally trivial and need not be globally trivial. 6 things to carry away. 1 exact implies closed always. The Poincaré lemma is the converse on a contractible region. The hypothesis is on the domain, and every closed form is locally exact. 2. The potential is constructed, not asserted. The homotopy operator satisfies dk plus kd equals the identity, for one form that is a line integral along rays. 3. The standard failures. The angle form on the punctured plane, and the solid angle form on punctured R3, which is a magnetic monopole. 4. For any closed 2-form B downstairs, omega minus its pullback is symplectic upstairs. Closed because B is closed, non-degenerate because the pullback is horizontal. The field deforms omega, not H. 5 Fibre translation by A takes theta to theta plus the pullback of A, and omega to omega minus the pullback of dA. If B is exact, that intertwines the 2 pictures. If not, omega sub B is not even exact. 6. The free Hamiltonian on the modified structure gives the Lorentz force, as does the modified Lagrangian downstairs, and the momenta stop commuting. For lecture 10, read Marsden and Ratiu, chapter 7, sections 1 through 4. Lagrangian mechanics in earnest, the Fibre derivative, and the equivalence of the 2 pictures.